Hello and welcome back. In today's video, we are going to study one-dimensional transient heat conduction problem. In the previous video, we studied pure uniform transient heat conduction where temperature was changing with time only and there was no temperature variation with spatial coordinates. So in this case, we are including now one spatial coordinate, that's one-dimensional transient heat conduction. Now for such type of problems, we have a model that we use is semi-infinite solid model. So what is this model and what are the practical systems on which we can apply this model? What is this model? Now, a body that has one surface and it extends to infinity along all the directions. It has one surface and it extends to infinity in all other directions, something like this. So this will be its surface and it will be extended to all the directions. Such a body is called a semi-infinite body. Now, a practical system that we can take as an example in this case here is, for example, Earth. Now, locally Earth is flat, locally. So, taking this as a surface and rest this extends to infinity. If we consider this to be Earth, so it will be a surface, local surface, and it is extending to infinity on all directions. Now this is the same infinite body. Now what we can apply this model is how we can apply this model and what we can achieve using this model is that when the whole system is at some initial temperature, say 20 degrees Celsius, and this surface is, suppose the condition on this surface is changed, suppose we maintain it at 100 degrees Celsius. Now taking direction perpendicular to this surface here, we will take it x, and this is the direction along which heat transfer will occur. Now what will happen is that the most important condition to which can be used to recognize whether the semi-infinite model can be applied here or not is that now this temperature here, now this temperature here is 100, the rest of the body is at 20 degrees Celsius. Now heat will transfer from this point and move forward along the x direction. It will move forward along the x direction, and after some time it will, the ecothermal equilibrium will be achieved, and this amount of thickness, when we compare it with the rest of the thickness of the body, if we call this xg, in which the temperature gradient exists, and we call it xt, the total thickness. So our xg here will be much smaller than x total. So for the body where this temperature gradient portion, temperature gradient thickness and the rest of the thickness, if we compare the both, this thickness here will be negligible compared to the rest of the thickness. So for the rest of the thickness, the temperature will be maintained. It will keep on to be at temperature 20 degrees Celsius. So the most of the portion of this body will not be affected by this temperature change here. So this is where we can apply semi-infinite model. So wherever we feel this, we can apply. Now, for example, suppose this is Earth and we want to make a house here. Let us suppose we want to make a house here. So, and we want to calculate, suppose, heat load of this house. When we calculate heat load of this house, we have to calculate the heat transfer through walls, through roof, as well as through this slab, through the underground slab, or through this slab on grade, or whatever it is. So this base which is on the ground, we have to calculate heat transfer through this, and for that we should know what is the temperature beneath the surface, beneath this ground floor. So that temperature we can calculate if we know the temperature distribution in this small depth of this Earth. we can calculate the heat load and all that for this house for energy efficiency purposes. So what we can do is we can see that this earth here with this is a exposed surface, and rest it is extending to infinity, so it is a semi-infinite solid. So it is a semi-infinite solid, and we are interested in temperature distribution in this small thickness, and for the most of the rest of the thickness, the temperature will not be changed. It will not be influenced by this temperature here. Suppose outside it is winter, it is say minus 10 degrees Celsius. Inside, average temperature of the whole earth suppose is 20 degrees Celsius. So temperature variation will occur for this negligible thickness. For rest of the thickness, it will be unaffected. So this temperature in this section, in this small thickness, we can calculate using this model. So moving on, what is this model? Now, what is this model about is that it is one-dimensional heat transfer, and the temperature changes with time. So it is something like xt that we need to find. So differential equation for this is d2t divided by dx2 is equal to 1 by alpha dt by dt. So one dimension, transient, this our equation. So when we solve this equation after applying appropriate boundary conditions, what we get is we get the value of x of t ultimately, which will be t surface plus t initial minus t surface error function of x divided by 2 square root of alpha t. This is the equation that we get for the temperature distribution with space and with time. Now we will solve a problem in this model, for this model, and we'll calculate temperature at a particular location at a particular time using this equation. And for this we have a problem: a semi-infinite solid with thermal conductivity this, density this, and specific heat this is initially maintained at 20 degrees Celsius, surface is kept at 100 degrees Celsius. What will be the temperature at a distance of this and from the surface after 1 hour? So we have to calculate temperature at 0.01 meter, and after time 3600 seconds, which is 1 hour, we have to find this is to be found. So we'll use this equation. Now this equation has, first of all, error function. Error function is like any standard mathematical function. We have some argument value, we find what is the error function of that argument value. Like sine of 30 degrees is 1 by 2. In the same manner, the value of error function varies between 0 and 1. It's not less than 0, it's not greater than 1. So now error function can be found using this. Suppose error function of some argument z can be found by definition. It is 2 divided by square root of pi integration from 0 to z e to the power minus t square dt. This is the definition, and 2 divided by square root of pi, and we do not need to find this integral. Its value can be approximately given by a series, which is z minus z cube by 3 plus z power 5 by 10 minus dot dot dot. We can take these three terms and we can get the approximate value of this error function. And if for our case we have to find z, and for our case z is this whole, which is x by 2 alpha t. X by 2 alpha t, or z is x divided by 2 square root of alpha t. We'll find this first. X is 0.01, 2 is 2, square root of alpha t. Now we have to find alpha first. Alpha is k divided by rho cp. K is 2.5, rho is 1500 according to the problem, and cp is 900. When we find this, we have 2.5 divided by 1500 divided by 900. We have 1.85 times 10 to the power minus 6, and it is thermal diffusivity meter square per second. So we have alpha, so that means it is 0.01 divided by 2, 1.85 times 6 times minus 6, and plus 2 minus 4. So we'll solve this portion and we'll get our argument 0.01 divided by, or better to solve root first. So square root of 1.85 into 36 into 10 raised to the power minus 4. What we are getting here is 0.01 divided by 2, and rest of the value we got 0.0816. So after solving this, 0.01 divided by 2 divided by 0.0816, what we are getting is value of the 0.0613. So error function of 0.0613, using the previous series we can solve this, and it is 0.0691, 0.0691. So this is our error function, and we can calculate this using this series. We'll put our z equal to 2 is known, pi is already constant, so this is 0.0613 minus 0.0613 power 3 by 3. In the same way we will get that value. So our t at 0.01 meter and after 3600 seconds will be t surface, which is 100, plus t initial is 20 minus t surface is again 100. Error function of that argument, which came out to be 0.0691. So what we have here is 100, 20 minus 100 is minus 80. So here 0.0691. So when we calculate this, we have 100 minus parenthesis 80 times 0.0691. We have 94.47. We have 94.47, which is approximately 95 degrees Celsius. So this is the analytical value that we got. Now what we'll do is we'll move to the COMSOL numerical solution. We'll calculate the same temperature at the same point and after the same time, and we will compare the two values. COMSOL will choose 3D geometry, heat transfer in solids. Then we will choose study time dependent because it's transient. Now we have to create geometry. So first of all, we have to keep in mind that it is one-dimensional transient. So transient, we will do it. We have done it like choosing time-dependent study. And for the one dimension, what we'll do is we have to make sure it is something like one-dimensional object and heat is transferring along one dimension. And rest of the dimension will be thermally insulated to make sure the heat transfers along one direction only. So we'll make a cylinder with radius very small as compared to its height, something like this. We'll right click the geometry, cylinder. We'll keep radius as 0.5 meter, and what will keep height 100 meters. We will position it along, we'll keep its axis along x-axis, and so this will be our geometry. So we'll heat up this side, we'll keep this side at 100 degrees Celsius, and curved surface and the back end will thermally insulate so that the heat is transferred in this x direction, but through a small thickness only because it is insulated everywhere. So what we'll do for that is we'll go to heat transfer in solids, then thermal conductivity will be user defined, and which is according to the problem 2.5. Then density will be, according to the problem, density is 1500, and then specific heat according to the problem is 900. So then initial value, initially the whole body is at 20 degrees Celsius, and which is 293.15 Kelvin. Now we have to apply the 100 degrees Celsius temperature. So right click 100 degree Celsius, which means 373, and we have to apply it at this end. Now if we see this end is blue, we can check. So this is blue because this is selected. Now, when I click thermal insulation, the rest of the rod is blue, which means the rest of the rod I have not applied any boundary condition on, which means the rest of the rod will be applied with thermal insulation by default, which is how COMSOL work. If we do not apply boundary condition to any surface, it automatically applies that with thermal insulation. So curved surface is thermally insulated, back end is thermally insulated. This is at 100 degrees Celsius. Heat will flow in this one direction, and it will flow through some small distance only, because everything is thermally insulated. So it has no driving lower temperature from this end. If this end were at lower temperature than 100 degrees Celsius, though it would transfer along the rod towards the other end. So next we'll mesh it. It is meshed. Then we'll go to study. We'll start time at 0. We'll keep time interval. We'll tell it calculate temperature at every 300 seconds and calculate up to 3600 seconds, which is 1 hour. So we'll compute. So once it's computed, we have our results here. We can change temperature unit to degrees Celsius, and we will check maximum minimum units and all that. So we have maximum temperature of the rod 100 and minimum 16.3. Minimum is somewhere 20 degrees Celsius. So the whole most of the rod is blue, which means it is at 20 degrees Celsius, not influenced by this temperature here. So only this little portion over here will show temperature gradient. We can see this little portion will show temperature gradient only, which confirms that we are on the right track towards using semi-infinite solid model. Now, next we have to find temperature. Next we have to find temperature. This is 0. We have to find temperature at a distance of 0.01 meter. So what we'll do is, how we do is a 3D geometry. We have to place a point at that location. So how we do it, we go to data set, we right click, we choose cut point 3D. 3D inside the 3D geometry, we have to cut a point, and it is at a distance of 0.01 along x, and it is at the center. So y will be 0, z will be 0. We'll plot it, and we have point at 0.01. At that point we have to find the temperature. So the data is in the derived values. We'll right click, we have to find temperature or any data value at this point. So it is point evaluation. We will right click the derived values, point evaluation, then data set. We will click it and we'll find our cut point 3D that we made. So here is cut point 3D. We can change unit to degrees Celsius for proper comparison. Then we will evaluate. Now we will have temperature at this point at all the timers, which will be tabulated here if I click this. So we have temperature at 0.01 meter, and that is at this point the temperature initially is starts with 91.611, then after 300 seconds 92 point this, then this, and after 3600 seconds, which is over time, at that point after this time it is 94.68. So it is 94.68, which is also approximately 95 degrees Celsius, which is the COMSOL result. So temperature distribution found analytically is 95 degrees Celsius, and it is found using a COMSOL, and that is 95 degrees Celsius as well. So this was all about today's video. Thank you.